Alright, so I just made some code here to plot some 3D vectors. Thought I would share it with y'all. The first thing that we need to do is import some modules. So we got Matplotlib, .pyplot, and NumPy. First, just some simple vectors. We want to add this fig set equal to plt, which is our matplotlib.pyplot.figure here. And that'll just make it easier for us to use that throughout the rest of our code. This is us initializing or like kind of defining our first graph. AX is our first graph. So when we do fig.addPlot, that's us creating a subplot. The 111 is like the position of that plot on our output, and we're telling that our program that it's going to be a 3D plot. We're defining our vectors, and this is the command here to make a vector. It's called quiver, which is pretty cool because the vectors kind of like arrows. So we say we're going to make a vector. This is our origin. This is our direction vector, which is the same as this. You just have to do it at each index at a time. We define our color and how big we want the arrow will be. We set our limits here, and we label our graphs. And there you go, just PLT show. And it looks very nice. If you want to get more complex, like I did down here, I'll skip this for now, but that's basically just a function that computes the dot product of two vectors. So this is the same kind of thing that we did before. The figure equals plt dot figure. This is us defining our first subplot again. Again, this is the position, saying that we're okay. It's 3D, it's in third dimension. And here we set some limits for our plot. And there's two cool things that you can do when you are graphing vectors is you can either define a start or an origin point and then put that in when you are defining your vector as your start point. So this is all our origin. So it's still just 0, 0, 0. And then this is also our direction vector. And then we label it. We just give it a name so that we can see what it is later. Like down here, you can see, okay, blue one, V, okay, that's what that looks like. That's what that one is. You can also do it without using this, like we did it up here before, just putting in zeros as our origin. And you can even do some math in here, some vector addition, if you will. You just have to do it point by point or index by index. So this is our origin for this one, and this whole thing is our direction vector. But for each point, we're adding each point to the other vector, the corresponding point. And then we just label it as such, okay, this is u plus v. This is also to keep things a little more manageable. The arrows on the vectors tend to get really big, so this just helps to keep it like a decent size for us. You can also do it for subtraction and things like that. And then we label stuff, label stuff, and we even make ourselves a little legend. That's what we saw down here. So now we have, okay, what's V? Well, it's that one right there. What's U? It's that one. Pretty self-explanatory there. But then we can make another plot, and you can make this on the same output, which is really cool. You just have to add another subplot, give it a different position, find some limits, and yeah, you do the same thing. I basically did the same thing. We're starting at a zero origin, but you don't have to start at a zero origin. You can instead say, okay, well, I want to start at where vector v ends, and then do the subtraction of u minus v. We're going to label it as that. And you can do that for all of them. And so that's what we did here. So we can see that they line up, and that's even like we know that we're doing our math right if we were doing it by hand. yeah, and then we just get our legend, everything. And now that we're down here, I'll talk a little about this dot product function. So the dot product, as we've gone over in our classes and everything, is it's the first part of a vector times the first part of a different vector plus the second part of the first vector times the second part of the second vector, all added together. So when we're calling this down here, I'm declaring the magnitude, but the magnitude of a vector is just the dot product of it times itself. So if we go back up here, kind of walk through the logic, is we get two vectors as our parameters, and so we set A equal to the first index of our first vector times the first index, or the 0th index of our second vector, so that'd be 2 times 0. For our second point, do the same thing, but with the first index, 3 times 5, and then C is the same with our last one, 1 times 4. And then we add all those together and we return it. So magnitude of U is 14, 41, all that good stuff. So this is what our graphs look like at the end. One more thing that I did was I wanted to see how we could plot functions, because you can plot functions in 2D. I wanted to see how you could do that in 3D. So we did this, just setting everything up, just like we've been doing. And now, instead of creating arrays with numbers for our vector direction, we just had an equation instead. So we had t, that's going to be in our z component, as we see down here when we plot it. X is going to equal sine, cosine. This isn't anything right now. I don't have it doing anything. It's just kind of there. I was testing stuff. So then when we plot it, we just say, instead of up here we were saying quiver, down here we'll say plot 3D, because it's a 3D plot. It's not a vector per se, because this could potentially go on forever, right? But a vector has at least like a certain endpoint. We're saying, okay, it's going to here over this period of time. Yes, then we label it, and let's go ahead and look at this one. This is the first plot that we made, and that's what it looks like, and that's what x is cosine, y is sine looks like. And then just another graph here, little graph as well, down here actually, where we just flip them, just see, okay, how does it look going the other way? And as we expect, it's just the opposite direction, still going up and everything like that. So yeah, I hope you guys enjoyed. I hope this made it clearer. I'll add this Jupyter notes as well. I'll share it with everybody that wants to if I can. So